counters and these kinds of things if you need more detailed insights into your code. You can do introspection. So you can actually query performance at runtime and use it for things like maybe auto-tuning and things like that. We haven't really looked into that much, but it is an option actually. Now, one thing we use Caliper a lot for is comparison studies across runs. So these would be things like performance regression testing, features like running your CRM tests, and eventually keep track of how performance evolves as we develop the code, or simply things like configuration and scaling studies. So Caliper is really good for that because it enables automated workflows and fits in with other tools like Thicket, as we see. So as I mentioned, Caliper fits into a kind of a tool ecosystem that we're developing here at the lab, in particular with Thicket. And here Caliper is essentially our program instrumentation and performance measurement component. So that's what's basically doing the performance measurements. And it works together with another little library called RDAC. So RDAC allows us to collect run metadata automatically. So these would be things like what machine is this running on, how large is the program, and you can also use it to input program-specific run information, like what input deck is it using, what is the problem size, and so on. And this really allows us to automate a lot of the parts of doing these comparison studies, like scaling studies and performance regression testing. Then we can load these combined Caliper and RDAC profiles into Thicket. And Thicket is kind of a Python framework for exploratory data analysis. So this really allows you to slice through these large ensemble studies that you can run with Caliper and RDAC. And yeah, do all these things like scaling analysis and so on. So that's the second part of the tutorial with the video concern and all the peers. Okay, so here are a couple of material links for Caliper. So Caliper is developed on GitHub, so you can see the GitHub page, the main GitHub repository down here. If you have any questions or issues to report, then the GitHub discussion page or the GitHub issues are the ideal place to do that. You can also contact me directly via email. And there's also kind of a little tutorial available on GitHub as well. So this covers the materials that I shall later the hands-on part. And you can actually install this tutorial material yourself on your own computer as well and just follow along there. Okay. So one more little organizational note. So if you have any questions, I think it's good to just post it in the chat. And I think Olga and Davey are going to monitor the chat and either answer the questions themselves if they can, or forward it on TV. Okay. So how do you actually use Caliper? So Caliper is primarily an instrumentation-based performance profiling library. So we do go manually into the code and mark regions that we want to measure performance for. So there are various macros and functions in Caliper that we can use to do that. So that is the first step. Now, on their own, these annotations don't really do anything to run performance measurements. We have to enable the Caliper measurement configuration. There are various ways to do that. So we can use environment variables like this static config variable, and we can actually also use an API so the program can itself turn on performance measurements if it wants to. And there are various measurements or measurement recipes available. There are really lightweight ones for just printing basic reports, or more complex, more detailed measurements that give you more information. Then of course we want to analyze our data, and depending on the configuration, Caliper can just like print out text tables or it can write files that you can then import into tools like Hatchet or Thicket, or managing or trace browser, for example. Okay, so as I mentioned, the first step with Caliper is usually the source code instrumentation. So Caliper actually started out as a source code instrumentation library. That's kind of its key functionality in a way. So there are various macros and functions for C, C++, and Fortran to mark regions in code. With the example here, which is like marking this init region, for example, the standard region macro. And there are various specialized ones as well. So we have kind of a phase macro as well. So phases are meant to be sort of higher level, broader package-based kind of regions that denote like a whole, program phase instead of just like really single code or something like that. There are also specialized macros for marking functions and units and so on. But either way, your code's going to have these macros and these instrumentation regions, and that allows Caliper to make measurements for that. But as I mentioned, they are not doing anything on their own. So the idea is that you can just leave them in your code, and if you don't have a measurement recipe enabled, they should really have all that much overhead. But now, if you do want to make measurements, then you can just enable these in runtime. So how do we usually go about instrumenting a code? So it's a good idea to be selective. So we usually instrument just high-level program subdivisions like kernels and phases and so on. And so this is not meant to really drill down and pinpoint performance bottlenecks at a really detailed file line level. So, but really to give you an overview of the logical structure of the program. If you do need more detail for your performance analysis, then there are options to enable sampling together with your measurement, and that will give you, for example, detail down to the file line level if you need that much. It's actually kind of an advantage of medical program instrumentation, because it really gives you control over what you want to measure, so you can really focus on either a specific thing or just have like a broad overview. So it's also good to use meaningful names. That's actually another advantage of manual instrumentation. So you can use names for your code that really are meaningful to you as a developer. So this is particularly valuable in the large C++ codes that we often have here at our lab. So we use complex C++ template-based libraries like Raja to get a lot of our stuff done. And with Caliper, we can give these constructs kind of immutable names. So in the example that there, you know that this is your dot product and not a weird simple name the compiler generated for this name. So it's really making performance analysis also easier for the end user. And it's always useful to just add instrumentation incrementally, so you can start out small and just annotate high-level regions, and if you need more detail for anything, just drill down incrementally depending on what you need. So overall, it really gives you a lot of control and allows you to get meaningful insights as developer, I would say. So which is especially useful for extremely large codes that we have, for example, at Cloud. Okay, so once we have these instrumentation regions in place, we can run performance measurements. And the easiest way to do that is to use one of Caliper's built-in profiling recipes, and there are a bunch to choose from. You can select these with this caliconfig environment variable. So up here, we're using the runtime report that will just print out the time spent in your annotated regions on the screen in the immutable text table. In an API program, it will actually go ahead and aggregate these times over all the API ranks. So you see statistics like the minimum, maximum, and average time rank in the region. So here's kind of a not complete list of these built-in profiling recipes. So there are a whole bunch for, well, simple reports as well as more detailed profiles that you can analyze and processing tools like Thicket. So we have the runtime report I mentioned. You can specifically look at loops between API functions, the kind of sampling, tracing, and then there are various configurations for connecting profiles for Hatchet and Thicket. The Caliper provides a little query program called Caliper. This can list all the configurations that there are with the --help option. Okay, so none of these profiling recipes are actually configurable, so you can give them additional parameters to enable, well, additional measurements or change the output options and things like that. And here's an example where we activate memory high watermark connection. So this will actually tell you how much memory you allocated in a function through malloc. And you can also redirect the output if you want to a file or to slip out something like that. So here's an example for another option. So we can do MPI function profiling, and in that case, Caliper will go and intercept all the MPI functions in your code. And then you can see how much time you spend in MPI wait, wait all, and so on in your code. Similar thing exists for CUDA. So the profile CUDA option will give you the time you spend in the CUDA API. So this will be things like how much time you're spending in CUDA memcopy, CUDA launch kernel, and so on. And we have a similar thing for HIP. And we also have analysis capabilities to actually look at the GPU activities. So that there are other options that tell you how much time you actually spend on the GPU versus your CPU. So that's, of course, really helpful for analyzing GPU-based codes. So there are a lot of these options, and if you use the Caliper --help, your configuration name command, then it will tell you all of the options that there are. So it's certainly good for you to get a little overview. So if anybody has questions in the chat, Olga or Davine, if we can forward them to me, that would be great. Or if you want to answer them, also good.
There's a couple, maybe I'll just read them to you and you can answer them.
Okay.
Is it possible to have a global overview of the app without targeting any specific region?
A global overview of the app.
Like maybe sampling, just without annotating? That's what I was thinking.
In principle, yes. So we do have a sampling configuration. So you do need to initialize Caliper somehow. So usually that would involve adding at least one region for, say, the main function. Or once you have that, then you want to enable sampling, you can do that.
And then is there an equivalent to for HIP, an equivalent for profile.cuda for HIP?
Yes, there is.
Okay.
So HIP is a little bit in flux, so they are changing their internal profiling APIs sometimes, well, not all the time, but they are changing it right now. So the current version is going to use the rock profiler or rock tracer SDK that is making everything up to rock 6.1. And with the next version of Caliper, we're going to mostly switch to the new rock profiler SDK interface, which is going to be in roughly 6.2 forward. But that should actually all be hidden from the user, so basically only be relevant when you build Caliper. Okay. So what else can we do? So I mentioned sample profiling. So if you need a little bit more detail about your program that goes beyond the limitations that you have in the code, the sample reports and sample profiles can provide that. So that will give you an overview of the functions that are called, so the actual function names, And it can also provide file and file locations where you're spending most of your time. So I saw another question what the format of the trace files is. Luckily we're right at slide. So you can collect event traces with Caliper. They are initially stored in a custom trace format or Caliper's own output format. We can convert it to the Chrome trace format that Federal and Chrome can read. So that's a good way to just collect and visualize little timelines for your program. Now, this doesn't particularly scale well, so it's not really the greatest idea to run this on like 1,000 MPI ranks and run for 5 hours. But for small examples, it'll work just fine. So for now, essentially, the trace formats that we support are the Caliper's own custom one that can be converted to road tracing.
There was a question from Cyrus too about the MPI services. If they provide you a global picture of all MPI calls, like aggregated.
Wait, what was that again?
It's in the chat. Will some services, one of the MPI options, provide you a global picture of all MPI calls?
Yes. So there's the MPI report config actually that will just provide a total overview of timestamp and all the MPI functions. And the runtime report provides you a little bit more detail and shows you where in your program you call them. Okay, so I mentioned you can actually forward Caliper to other tools. So a good example is NVPX, that's NVIDIA's annotation API. So we can automatically convert our Caliper regions into NVPX regions and then forward them to NVIDIA's own profiling tools like Insight and NCU, and also the overview prof, because I haven't updated the slide in like 5 weeks. Okay, so then I mentioned the little Caliper program. So you can actually use that to look at your performance data as well. So a lot of the Caliper tracing and profiling formats write this custom .cali format, and Caliper can read it. And you can write like SQL-like queries to slice through that performance data. It's actually pretty powerful, just like takes some getting used to the syntax of the query language. One more thing I want to mention is the config manager API. So this is kind of a unique capability of Caliper, I would say. So you have an API where you can configure and enable and start profiling through the program itself. So that's built through this config manager class. And you can give it profiling recipe strings that basically use the same syntax as the Cali config environment variable. And then that way you can configure your profiles through the program itself and then stop profiling as you like. So this is kind of useful to, enable profiling through the program itself. So for example, you can use command line arguments now to enable profiling, or just have it enabled by default all the time. Okay, so if none of the built-in profiling recipes do what you want, you can also kind of configure Caliper manually. So pretty much all of Caliper's measurement functionality is organized in little modules called services, and you can kind of mix and match all these services and configure them independently in any way you like. And that way you can construct pretty complex analyses. So in this example here, I think we're tracing memory copies between GPU and the CPU, but we can map those to, both the code regions where they happen, and also the named memory pools that would involve these transfers. So this allows pretty unique and specialized insights. So we're not going to go to this level of detail in the rest of the tutorial, unfortunately, but just kind of demonstrating the kind of things that are possible with Caliper. Okay, so one more thing I want to go into is how we're actually collecting data for Thicket. So Caliper is kind of currently the main data provider for our comparison and ensemble analysis that we do with Thicket. And yeah, this is how it works. So essentially, we need an instrumented Caliper program. And in addition to that, we also need metadata annotations in there. So this is where this little ADIAC library comes in that I'm going to talk about a little bit later. So with ADIAC, we can also put additional kind of instrumentation calls into the code that collect kind of run information that describe what this program run is doing. So in particular, there are, well, we can say, well, where is the program running on? What is the number of API runnings? Who is running it? When did we start running it? And so on. And we also can add program-specific information, or like what input deck am I using? What's the problem size? But also give it some kind of global performance metric at the end, like a figure of merit. So this goes into the program as well, and this is particularly important for doing analysis with Thicket, because that will then allow us to slice through all the different performance profiles that we collect. And finally, of course, we need to run the program, collect performance data. So we're typically using a recipe called Spot. So this will write a little profile file. And Spot was kind of the predecessor of Thicket. So yeah, that's essentially what's producing our data. This again produces one of these .cali files, and you can put a whole bunch of them for an entire kind of analysis that you want to do. For example, for a scaling study or so, into a directory, and then you feed this directory to Thicket and can slice through all this data that you collected. Let's talk a little bit more about ADIAC. So ADIAC is a little C and C++ library to record program metadata. It provides kind of two kinds of calls. So there is kind of built-in functionality that collects a bunch of commonly available metadata information. So that would be like the system information on what the cluster is running on launch day, which running it. And then there's this key value interface that allows you to put custom information about your particular program as run metadata into the application. So in this case, we're using it to add several input parameters that we got for our input deck, and the algorithms that we use and so on. So this is essentially what enables us to automate a lot of the ensemble analysis and Thicket later on. So here's a bunch of the information that ADIAC can collect on its own. So there's things like username, launch date, what's the executable, what's the command line, what are the libraries, and it's not an exhaustive list actually. So it also gives you what MPI version are detected and so on. And now there's like a ADIAC collect all call that will just collect everything, like connect things easier for developers. So then again, I mentioned we have this key value interface. So there's one in C++ and one in C. So it's pretty simple. You just give it a key and a value in the C++ interface. It collects it supports a whole bunch of different data types. So all the standard ones like ints, strings, doubles, and so on. There are a couple kind of specialized strings that you can provide and say, well, this is a version or this is a file path, and that can be helpful. And you can actually also put in more complex data types, so you can put in vectors, lists, and so on, and structs. And you can actually, go kind of nuts and put in, absurdly nested data types as well, if you are inclined to do so. But of course, that also makes things more difficult on the analysis side. So it's usually better to keep things simple, I would say. So we have a simple or a similar name value interface in C, and that also gets a key and a value. And here we're kind of using a printf style encoding, so you can specify which data type you want through like these little printf style descriptors, like a percent D is an integer and the percent F is a float and so on. So it's actually kind of neat. Okay, so that's that for the slides. Are there any questions in the meantime? If not, well, let's jump into that. So let me briefly point out again this spreadsheet here. So we've set up a bunch of AWS instances, and essentially you can pick yourself a slot in this Google document that should be shared in the chat somewhere. So essentially what you do is you SSH then with your username, which is like radius 1, 2, 3, 4, and so on, and this IP address that we have listed for your slot. The password is the same as the username. Note it's a double S in this radius. And yeah, for the Caliper part, we're just going to use SSH. So you SSH into the host, and then little thing to note, you can run this source/op/Caliper tutorial/setup-env.sh script, and that should load the materials that we have for Caliper. Okay. That is hopefully somewhat clear so far. Okay. So let's jump into this thing. So I'm on my own little AWS instance. By the way, can you read this? Is this like large enough text? Okay.
I think the text size is good. One person can log on up, but I can see if I can help.
Okay, sounds good. So again, you can run this source/op/Caliper tutorial/setup-env command that will load the path that we need with all the breakdowns into our environment. And actually, let's jump into this directory. So here we have Caliper itself, and we have a bunch of little example applications. So the simple one, really basic, is this basic example that we have in /apps. And let's please look at the source code here. So this just demonstrates how you can add Caliper annotations to your code. So there are a couple different methods that we can use. So we have a few specialized ones, like CXX mark function that will mark this particular function. And in C++, you only need to put that at the beginning of the function, and it will shows itself automatically at the end. In bar, we have the same thing, but in the C version. So here you need to mark both the beginning and end of the function. And yeah, this particular example also provides a couple of instructions that you can use on how to add a config manager API that will automatically run or start profiling for you. And there are a couple more annotations in the code as well. So we have setup region mark, and we also have a loop mark here. And for the loop, you can also mark iterations, and that way you can do kind of time series profiles and iteration profiles as well. And okay, we can run this basic example program, and as I mentioned, on its own, not running much. If we read our Cali config variable, we can, for example, print the runtime report. And that will then, well, print the time is spent in all our annotated function on the screen. One more thing to note, I didn't really go into how you actually build the program with Caliper, but if you're using CMake, we do provide CMake package support for, or we provide CMake packages for both Caliper and ADIAC. So you can do a find package Caliper and a find package ADIAC, and then make the corresponding targets, which are just Caliper or ADIAC, quote-unquote, on ADIAC, for Caliper and ADIAC respectively. So that should be easy enough. If you're not using CMake, you can just link. So Caliper is now built into a single library. So you just need the caliper.so, and that should be fine. Same idea. Okay. So I mentioned our runtime report makes a few additional parameters. So kicking off, for example, we can do region count that will count the number of times a region is called. And whoops, that's actually produce them. Slightly too large output here. We can redirect it into the file. Right. That's it. Oh, we are. Yeah, it's usable if you are in a writable directory. If you want to direct your output to file, then we can look at that as in a slightly better form. Well, and now we see the number of times a region was called. So in this instance, we're actually using kind of the MPI node of Caliper. So if Caliper is built with MPI support, it will automatically for the output reports enable MPI mode. That means it's gonna try and aggregate everything in all MPI rings and give you additional statistics, like the minimum, maximum, and average time, as well as the minimum, maximum, and average number of calls. There's actually another option that we can use to disable that and turn activate and cross ranks off, and then it'll bring a little more simple report for just a single rank run. Okay. So now I mentioned we do have this MPI support, and there's a little MPI program here as well. We have meters instrumented. So this is, well, a venerable proxy application, I'm saying. So it's not really meant to do actual performance studies anymore, but instead it serves as like a little MPI demo. So let's actually got that. Let's see what we can do. So actually, I can demonstrate the MPI report. So this will just print the total time that we spend in MPI functions in our code, and you can run into choose that. And we're gonna use just like a few little or very few iterations to make this that one to draw. But yeah, that will then show us all the time you spent in all the different API functions in the program, as well as their counts. So how many times you call each of these functions, well, kind of in statistics as minimum and maximum. So the top line here doesn't have a function name, is all the time that we spend outside of MPI. So in this case, we have like 80% of the program time spent in some kind of computation, and the other 20% in all these various MPI functions, where MPI may all stand creating the hotspot here. So we can also integrate the MPI profiling into our runtime report. So we can do that.
David, we also have a question about, can Cali queries show what configuration was used to produce a Cali file? Basically, what?
It can actually, yes.
Okay.
Let's do that. Actually, let's start with that. Okay. So we're also collecting metadata with each one. So we've also annotated in bash brings a bunch of ADIAC calls. And this range metadata option will actually show us what they are. Like this again. Okay, so we're running that again with 8 processes, 4 iterations, enable the metadata printing, writing into a report.txt file, and see if it works. Okay. So, yeah, by default, Caliper will actually append things to an existing file. Now, so we still have the output from our previous run up there, but that's fine. So here's a bunch of metadata that we collect. So we see things like the MPI, job size. We record the Caliper version actually. We record things like the figure of merit in English. So this block of things is essentially things that we collect through RDAC. So there are things like the figure of merit, which is kind of a total performance figure on this particular run. We collect things like the compiler, who built the program, various input parameters that go to English. For example, our four lists that we have here, we collect things like the NPI library, library version, the NPI standard version. And somewhere out here, we also, so from this Caliper channel variable, we can basically tell what configuration was executed. And we also record all the additional options that were enabled for it. So in this case, it was the print metadata, our option to append outputs, which is auto-enabled. And that we wrote our report sheet. And now here we have the actual Lulesh performance profile. With again the MPI statistics, so we find yeah, Lulesh is pretty well balanced. So maybe if we're looking at the other but we should have the time increment function. So there we see that the minimum, maximum, and average time are somewhat different, because well, this is where we have a collective function in the end. And that's picking up all the load balance or the load imbalance that exists in your program. It's why it's getting different minimum, average, and maximum times. Okay, so what else is there? So as I mentioned, we can profile MPI functions and put this in our runtime report. And now we should see all the MPI functions that we have. And for example, how much time we spend in this audit call, how much time we spend in wait all, in which particular communication region, and so on. So you also see that by default, these output or the runtime report supporting exclusive times. We can make it inclusive times as well. And actually, we can also show that we also have config manager support in Lulesh, so we can use the command line, but we can use command line arguments for Lulesh to actually, I think, also might make things a little easier. Oops. And I've enabled this through this -B flag here, Lulesh, but of course, this is always actually application code for bit to use. And let's try the inclusive. So this will give us inclusive times. There are also options for, single region count already. We don't need to do that again. But yeah, so now we're calculating inclusive time. So the time in main is the time we spend in the program. And then, we can see in our hierarchy where we spend most of our time. So there are also additional kind of little statistics for MPI that we can use. So there are MPI, massive size, I believe, is one thing. I'm getting a picture of API for them. Oops. And one into all this whole style. Okay. Edit. Okay, so this will give us statistics about the number of bytes we're transferring in API. So this works for our, well, how many bytes did we send and receive? That's actually a good point. So MPI is intercepted or can be intercepted by Caliper automatically, so you don't need to annotate all the MPI functions individually. The same for all the other APIs that we can intercept automatically by CUDA and DIP and so on. So anyway, we can see that we get like statistics of how many bytes we send in each of our MPI regions here. So this particular I sent, well, one rank was only sending 8 bytes, whereas one rank was sending over 7,000 in this particular region. So it gives you a bunch of little statistics about MPI communication. Okay. So what else do we have? Well, as I mentioned, we can run Caliper dash help with one file report, for example, which will give us all the different options that are available. So there are quite a lot for the runtime report. Now, not all of these are necessarily active, and because some of these depend on certain build options. So in this case, we're not going to have the CUDA and DIP profiling as well. This is the GPU build. But yeah, a lot of these should be active actually. Okay. So one more thing is, I've mentioned we have different annotation macros, and now we have a way to, for example, distinguish higher level regions from, well, normal Caliper regions. And if we only want our report to include the higher level regions, we can include this level option. Oops. If we use this to phase, for example, then it's a bit right. And we should only get, well, information for very high level regions that I've explicitly marked as a phase in dash. So this is not just the time increment, and these two Lagrange functions that execute. So basically measurements are only made for these particular regions. They're actually just 3, but we still see where in the hierarchy they land. So we still see that they're on the main relational cycle. Okay. So as I've mentioned, there are quite a few profiling, well, more detailed profiling output options available. So we can, yeah, collect data into a file that we can then read in Hatchet or Thicket. So, for example, we can use plot config. This is what we would use for importing data into Thicket. Spot also has a bunch of options that basically can use all these different metrics that the runtime report can also use. So, for example, you can enable MPI profiling for it. We can take a little region count that should actually be aggregated by default by now. And we can do things like MPI message size. And we can write a particular file, also aggregating. And by default, it will actually auto-generate a file name based on the current file. So let's do that. We should have this .cali file, and this package value where we can look at it. If you just wanted like a little quick overview of what is all in this particular file, we can use Cali query with this -T that will print a tree-based table like the runtime report does. And we should see that it's basically using very similar output to what we get with the one-shot report, only it's readable in Thicket and so on now. So yeah, again, here's all these metrics that we collected. So now we have our all the time metrics, so both inclusive and exclusive ones in this case. We have the number of calls, we have these MPI message sizes that we wanted. So we get all this good stuff now in the file that we can load into Thicket. And actually also look at the metadata that we collected. Well, it's not going to be pretty, but there are various output options where you can format this metadata that we collected with ADIAC. Now, some of that is pretty large, so we usually collect all the different libraries that we built the program with. And yeah, that's like a lot of stuff. So the output isn't really quick here. But we can also use different formatters like dash J will use a JSON file that we can parse automatically. The other options that we have are a Hatchet region profile. Which I do a similar thing, well, a somewhat similar thing to Spot. So the difference between the Spot recipe and the Hatchet region profile recipe is that the Hatchet region profile will actually collect for MPI rank data. So in this case, we can look at every rank individually and see what it is in. And again, we can use Caliper into HT to look at this data. It's going to be that lot, probably. And yeah, now we see that we have all of our data, which, well, we should have all of our data for all of our individual ranks. So this column here, the first column is going to be MPI rank. Then we're going to have the time for that. If you want to slice through that, we can use all of these Caliper queries. You can see which kind of attribute we have in our file. With this, it's going to be quite a lot because all these the metadata things are individual attributes, and then we can build a query with that. So again, I mentioned that query has this little SQL like with a bridge that we can use to construct queries. And one option that you can well, we can, for example, just print the time in MPI all reviews for each rank. Right, our MPI function, well, list all reviews. So this way, that should allow us to mix. Okay. Oops. But it's not available to output its own format again. What is slicer? It's a tree. Okay. So so with this query, we can essentially list the time that we spent in an MPI all reviews. Because we basically just selected all the paths that have an MPI all reviews in it, which is like one outside of the main function somehow, and the one inside the time increment functions. And then we see this data for each MPI rank.
We have a question about that query, David. Can you describe what all the sums mean?
That is a good question. So the sums come from Caliper's own aggregations, and in these profiles there are a few different subsequent aggregation steps. So first of all, when the program runs, it aggregates all the times for each function instance. So if you call our all reduce the mean that we're doing, then we record the total time for that. That will be the first sum, the innermost one here. And then we're doing one per rank aggregation of this data. So that will be the second sum, which in this case is not really doing much, but we can do other operations there. For example, you can make this an inclusive sum, and then, well, basically a inclusive time aggregation. So you see that the total time of the function, including all its children, for each individual rank. So in this case, that's the second sum. And then the third sum would be aggregating this all MPI ranks if we were doing that. So because we're actually grouping by rank, that's not happening. So that's actually kind of a no-op in this case. But if you're actually leaving that MPI rank out of the group by, you just get the total time, and that's then the last sum that we actually get. So now the single value, which is the sum of all these. I hope that was somewhat clear. I know it's like a little tricky to build these queries and understand kind of what's doing under the hood, but that is sort of what it's doing. Okay, so I think we're almost at the top of the hour, and I think we wanted to have like a little 10-minute break or so between the two parts, or maybe like 5 minutes, I don't know, before David is done and talk about Thicket. I'll still hang around so I can monitor the chat and so on. And well, if you have any questions, just put them in there. And well, in the meantime, feel free to play around with Caliper or the command line here.
So I'll be talking more about these programmatic analysis tools that you can use to analyze the data that you gather with tools like Caliper that David just talked about. So mostly today I'll be talking about Thicket, but as we mentioned previously, we'll be talking a little bit about Hatchet as well. So I will get started. As a quick reminder, if you missed this in the beginning of the tutorial, there are other Radius tutorials going on right now, so check those out if you haven't already. Thanks for putting these on, the Radius team. And then similar to how David ran his, feel free to ask questions throughout. It's hard for me to see the chat, so if you paste them in the chat, Olga and David will be monitoring that, and they can help answer your questions. And if not, they can interrupt me and we can talk about it to the whole group if needed. I'll be following a similar structure as David as well. So we'll start with a presentation overview of Thicket and a little bit about Hatchet. The slides, if you want to follow along, are available online. If somebody can paste that in the chat, that'd be helpful. And then we will be switching over to a hands-on tutorial. And in this case, it's going to be Jupyter Notebooks. So we'll access it the same way, or differently, but from that same document that we used for the Caliper tutorial. So I'll go over how we can access that, but basically you'll click on the URL and do some things there. So the tutorial will be Jupyter Notebooks that will just run and follow along, all in a containerized environment. So with all the dependencies needed and some data so we can look at and analyze and run. And then also, we do have this mailing list we're planning on setting up to send out release notes in the future. So if you're interested, here's our short little bit.ly link. You can add your email there and sign up for our mailing list, and we'll be sending out exciting news. Okay, so get started. Let's go back. Okay, so really the challenge that we're trying to solve with Thicket is conducting performance analysis on complex HPC ecosystems. So as you know, if you run any HPC software, there's hardware that's growing increasingly complex, and we need to look at things like the strong scaling and weak scaling of our applications across different rank counts or something like that. We also want to look at the impact of changing application parameters and how that might affect performance. So these might be application parameters specific to an application. We also want to look at the impact of our choice of compilers and optimization flags, optimization levels that we use when we build our code. And then also performance across different hardware architectures. So if we're moving from a CPU-only system to another CPU-only system, or if we think we want to move from CPU to GPU, comparing the performance across these different architectures is really useful. And then we also want to look at different tools. So there are a lot of different tools that measure these different aspects of application performance that we need to be able to interface and ingest this data. So as David mentioned, one of those measurement tools is Caliper. So sort of how this works is Caliper measures, you annotate your code with Caliper, and then you can get those performance metrics. Another tool that does this is NVIDIA Insight. And so being able to read in that data and generate generate the call tree profiles, and being able to ingest that data is our goal. So we want to be able to analyze and visualize the performance data from those different sources. So our big picture solution for this is here's sort of the flow that I mentioned. So step one is to run your code with these measurement tools, and those generate a certain type of output. That's step two, those call tree profiles. And then step three is loading that data into a Thicket object. So the Thicket object is made up of 3 different tables. That is the performance data table, which is all the performance metrics, things like time spent in a function, metadata, which David showed you a lot of examples of the metadata, how the application was run for that particular run, and then as well as aggregate statistics. So if we want to do comparisons or order reduction across an ensemble of many different profiles, then we can aggregate those into a separate table. And then once we have this Thicket object, we can conduct all of this exploratory data analysis. So we have a lot of support for built-in functions here that are basically made available as soon as you have your data loaded into a Thicket object. And since Thicket is written in Python, there's also a lot of third-party Python libraries that you can leverage. So so this is useful for that, to do things like creating performance models, manipulating your data and filtering it, and clustering your data as well. I feel like there's something else to say. Great. So what do profiling tools collect in each run? So if we're just thinking about one run of an application, what is generated from that? And one of the aspects is this call tree. So we know that, maybe our first function is main. Main calls foo and bar, and then bar also calls baz. So that's our call tree for that application run. And then we also have performance data. So each of those functions has performance metrics associated with it. So these could be cache misses, these could be time spent, flops, or memory accesses, things like that. So David showed a lot of these as well that Caliper can measure. And then the other thing is this metadata. So it might show who ran that, what architecture it was run on, the launch date that it was run. It could also include the build information, so compiler versions and flags, as well as any runtime information. So the command line used to run, different problem parameters, number of MPI ranks. So we have a lot of different data for just a single run of an application. And so as I mentioned, Thicket builds upon Hatchet's graph frame data construct. So if you've ever used Hatchet before, Hatchet graph frames are basically made of 2 components. The first is a graph. So the graph is basically the way to store the call tree relationship, and store the relationship between those parents and the children. So we again see here, main calls solvers, solvers calls MPI, MPI calls PSM2. So Saving this data structure as a graph allows us to maintain that parent-child relationship in the call tree. And then each of those nodes in the graph corresponds to a node in the data frame table. And so for Hatchet, and for Thicket, basically these data frames are native pandas data frames, so you can render them the same way that you would with a regular pandas data frame. So you can print those out and everything. But basically each node in the graph corresponds to a row in the data frame, and then you have the metrics associated with that, the performance table metrics. Okay, and that's a two-dimensional table. Oh, and if you are interested, we're not going to go over these today, but there are other links to information on Hatchet. So there's a Hatchet specific tutorial and the Hatchet GitHub repo. So you can look at those if you want, but we won't be doing those specifically today. Okay, so if we want to visualize Hatchet's graph frame components, we can print those out. So the graph frame object is this GF. And then if we call print graphframe.tree, we can actually print the call tree or graph in this format. And this is basically the default coloring. So what the number is here is one of the metrics that is stored in the performance data table, and then the node name. And the coloring this is the default, but this is customizable, so you can change this coloring schema as needed. And then, like I mentioned, the graph frame data frame component is a native pandas table, so you can print that the same way that you would a pandas data frame. So we can see each node here and the node name and the metrics. Okay. So Hatchet is really useful for comparing two graph frames. So basically, like if I want to calculate the speed up, so if I moved from if I ran once on the CPU only, and then I ran once on a GPU system, I might want to calculate what was my actual speed up achieved, and I have two different profiles from those two different runs. I can actually conduct divide graph frames just like this. And the first step is to unify these two trees. So if we don't have the exact same call tree in each graph frame, then we need to make sure we combine those. So we have foo calls bar calls forge, and then foo calls bar calls baz and grow. And we need to combine those so that we know bar would call forge, bar calls baz and grow. So that is done first, and then the output here in graph frame 3, so it's on the left like you would assign it to the new variable, is the result of that unify and then divide. So once you, I think there's an animation here. Yeah, great. So once you unify the call tree so that you know you have the full call path, you can just perform a straight division. So we see that bar here, the first run on CPU or whatever is 6, and the next one is 3, and so our speed up would be 2, calculated over here in graph frame 3. And then what do we do with those nodes in the graph that don't exist in both trees? We assume nans for like these values in graph frame 1, and then the division by nan results in a nan here. And then these little green triangles are basically indicating that these nodes were found in the right call tree, but not in the left call tree. So that's why you have a green arrow pointing to the right. If they were found in the left, you would see this red arrow pointing to the left. So this just indicates where the data came from in your previous statement. And you can do addition, subtraction, and multiplication in the same way. So the first step, again, is always to unify the call tree and then perform the math. Okay, so how does Thicket relate to that. So Thicket can compose performance profiles together. So Hatchet is really useful for looking at one profile, for comparing maybe two profiles. But as soon as you try to start scaling, it becomes unwieldy. And so Thicket's aim is to sort of fill that gap. So you can imagine you have two profiles here. Profile 1 contains the metadata, who ran it, where did it run. You have your call tree as well as your performance metrics. And then you have profile 2, also containing the user and platform, the call tree. And in this case, it's the same call tree and the same performance metrics, but obviously here different values. So these are assuming like multiple executions of the same application. Maybe you just use different build settings or different problem size or something like that. So basically we have the same application, but different performance metrics. And I guess it's worth noting here that Thicket can handle slightly different call trees, so they don't have to match exactly. And you would just get, nans or whatever in the metrics where you don't have that node. But in this case, in this simple example, they are the same call tree. Okay, so we have profile 1 and profile 2. We want to compose them together. Now we have our performance metrics table looks like this, where we have one node for each of the call tree nodes, right? So each node name here becomes one here. And then we have a second index level, which is the profile that it came from. And so this is basically a multi-indexed data frame where we have the node, each profile ID, and then the performance metrics associated with that profile get put in separate rows. And since these have matching call trees, we have all of them here, and those just get composed together. Similarly, the metadata gets composed. So in this case, we just have two rows, one for profile 1, one for profile 2, where we would have who ran that profile and which platform it ran on. So all the metadata fields get added together in that way. And then finally, we know that the third table within a Thicket object is this aggregate statistics table. And so in that case, same call tree, we have each node in the graph here, but we don't have that second index level, and we just have the performance metrics aggregated across both of these values. So if we were looking at the average cache misses, we have one value now here, which is 20, which is the average of 24 and 16. So that's how those get composed together. And now we have basically one Thicket object that contains multiple profile runs. Okay, and then the Thicket components are interconnected. So what this means is when you perform a filter function or manipulate in some way one of the tables, the other tables that are in the Thicket object will follow suit. So we have here our metadata again. We have two different users for each profile run on the same platform, and then we have our performance metrics table. Again, here, I guess one of the ideas we like to drive home is that this metadata, we really encourage users to add as much metadata as possible when they're collecting their metrics, because it can be really useful for filtering and sorting and organizing and manipulating your Thicket objects later. Okay. So, yeah, great. So if I want to filter on, I just want to look at the performance metrics for data that was generated on LLNL by Bob when Bob ran it, I can filter on the metadata table. So I'm going to say, okay, give me only the data that was run on LLNL by Bob. My new metadata table, my filtered metadata table will look like this, where it's just profile 2 now. And my filtered performance metrics will match where I only have the nodes here and the profile 2 data now. So if I generate, for an example of 2, we just composed them and now we're filtering. But when you have many profiles, this is really, really useful. Oh, yeah, and this is what I said. But the metadata fields are really useful for this. So if you're using Caliper and plan on using Thicket, we really encourage the use of generating as much metadata as possible about your specific run. Okay, great. So now Thicket enables exploratory data analysis of this multi-run data. So we talked about the Thicket object. We have the performance data table, the metadata table, and the aggregate statistics table, and how Thicket can compose the data from different sources and types. So if we have different MPI runs, right, from different profiles, different number of MPI ranks, each of those can be stored as a different profile in our Thicket object. We could have runs with different application parameters all in one Thicket. We can have runs with different compilers and optimization levels, different hardware types, and different performance tools. And all of these could be mixed together in one Thicket object. So we could run all these experiments and have these in one Thicket. And then being able to do this exploratory data analysis, allowing manipulation of the set of data, so filtering, aggregate statistics, visualizing the data set, perform analysis on it, build models, performance models for that data, and also leveraging other third-party tools. And this is a growing list of capabilities. So we're actively developing Thicket. And as requests come in for other functionality, we're constantly adding to the capabilities here on this performance analysis side. So we'll go over some of them today, but just know that if there's things you're interested in that we don't support yet, we do always welcome requests and love to hear what things you all need. So I'm going to go into, I guess before I start the case studies, are there any questions? I saw there was some activity in the chat, but I couldn't really see. So if there's any questions that I should address, I can do that. Otherwise, I'll move into these case studies. Okay, sounds like we're good. So our first case study is on the Raja Performance Suite. So the Raja Performance Suite.
Maybe.
Oh, yeah, go ahead.
Sorry, hold on. Let's maybe pause for a second. So Alex had questions, and I think they probably refer to your earlier slides.
Oh, sure. Yeah.
So he was interested in the computation of basically the slide where you showed the division of two graphs.
Yeah.
Maybe go back to that.
Sorry.
Yeah, so Alex, this example doesn't show to you that you can basically you don't just divide the two graphs. You tell which metric you're looking for.
Yeah.
Right, and so you can pick. So when you have your performance data, right, you can take a look at what has been collected. You can simply see what columns are available in that data frame. So can you forward to that, maybe, Davey, to the performance data? Right, so you can see which column names are present there, right? And there's always going to be time, but there could also be hardware counters that you are collecting and so on. And you can apply those operations to any of those columns, right? So any numeric columns that you have present, right, you can use in your analysis. And so it's the way that I would explain this is you are deciding what analysis to do. And this is a tool that's making it possible for you to do the analysis you're interested in. Does that help? So it's not that you're dividing graph frames, you're dividing the actual values in the, you're dividing the actual values that are the data that's present in your graphs, right? So that these numbers are coming from those metrics. So the key thing here is, right, what's happening in the background is that we're checking whether these we're checking whether the nodes are present in the graph frame, right? And so if they're not present, you will get nans, you will get an appropriate value, right? But this check ensures that if your nodes don't exactly match in the two trees, you still have the correct answers for the nodes that are present. And then for the ones that are present in just one, you'll get the nans or whatever is appropriate.
There's probably a lot of examples of this in the Hatchet tutorial.
Yeah. I think hopefully it'll become more clear. So I think we can let you keep going, Davey.
Okay, sounds good. Yeah, just moving now. Okay. So case studies. Raja Performance Suite is from here at Lawrence Livermore, but it's an open source suite of loop-based kernels that are commonly found in HPC applications, and they're basically implemented with the Raja backend and also the native programming model backends, which allows basically this showcasing of all these different programming models, and being able to run those on different hardware. So we actually don't have a link to it, but that would be helpful. But you can find that on the GitHub. But basically for this case study, we did a total of 560 different application runs that included varying a bunch of different parameters. So we ran on 2 different clusters. We ran on a CPU only cluster, and we ran on a CPU and GPU system. And then we also ran 4 different problem sizes. Oh, you can see here we ran on Quartz and Lassen. Sorry, these are the 2 clusters. So Quartz is the CPU only. Lassen has the GPUs. And then we had the 4 problem sizes of 1 million, 2 million, 4 million, and 8 million. And then we had 3 different compilers we used, as well as 4 different optimization flags. You can see here, Clang, G++, O1, O2, 3 different compiler flags. We ran these with 3 different programming models. So the sequential sort of baseline, OpenMP, and CUDA. Those are shown here. So the Raja variant is basically one of the many different programming models that Raja can compile to and run. So, and then we have 3 different performance tools that we gathered metrics from, including Caliper, PAPI, hardware counter metrics, and Insight Compute. So all of these different variations were run within these 560 runs. So if we want to compose the data together from across different platforms and different tools, this is kind of what that looks like. So we start here with a Thicket object that was basically 2 different problem size runs on Quartz, the CPU machine. And in this case, we used I think it was PAPI to gather the top-down analysis bottleneck metrics here. Reps is a Raja performance suite parameter, and also get the exclusive time. So we have one Thicket object that's made up of these CPU runs, and then we have another Thicket object that's composed of 2 different GPU profiles. Excuse me. So again, same problem sizes here, 1 million and 4 million, but we see that we have GPU metrics that came from Insight Compute. Actually, the time here came from Caliper, and these metrics come from Insight Compute. So you can see we have 2 different platforms, one Thicket object that was run on the GPU, and then one that was CPU. Let's see. So if we want to compose this into a single table, basically those get composed together based on these node names, right? So these are the actual Raja Performance Suite kernels that are implemented in these different programming models. So it's from the apps group, and the actual kernel is the nodal accumulation 3D or evolve 3D in these cases. So we'll basically combine these on the node level and extend the Thicket object to encompass both of these. So you can see here that we have our nodes here, we have our problem sizes, we have our CPU metrics, which came from this Thicket, reps, the top-down analysis metrics, and then the GPU metrics here. So, yeah, that's what I'm going to say about that. There we go. GPU metrics, this row gets added here, and they're basically extended next to each other because they match based on problem size. Okay. So now if we want to do some analysis on like a more complicated example, so we want to do these four types of profiles side by side, and we want to compare the CPU to GPU performance. So we want to look at the speed up again, moving from a CPU only to a GPU system. So number one here is basic CPU metrics that we get from Caliper. And then number two here is extended to add these top-down metrics that I mentioned, and we'll go into a little more about the top-down metrics later, but these come from Caliper with the PAPI service enabled. So the reason we don't do these together is because PAPI actually, when we use the PAPI service, it introduces some overhead to actually collect those counters and make those measurements. And so we want to have the sort of the bare runtime without that performance the measurement of those metrics not included in that runtime. So that's why we have the time here from without PAPI. And then we similarly, actually, in this case, we have the GPU runtime from Caliper, and then we have the GPU metrics with the measurements from Insight Compute. So things like the memory throughput, DRAM throughput, stream multiprocessor throughput, etc. Okay, so then we can create, these are all our measured metrics, and then we can create this derived metric column that is the speed up. So we can actually look at the time spent on the CPU divided by the time to complete on the GPU, and that gives us our speed up column here. So then we can look across and say, what metrics maybe contributed to the fact that apps Vol 3D had better speed up on the GPU than the Hydro 1D. So we can look at that type of analysis. Okay, we can also manipulate our data and filter it using call path queries. So we have a pretty robust query language, and actually that paper with a lot of details about that is linked down here. So if you want more examples about how our query language works, they're in there. And we have one of the notebooks in the tutorial is also has more on the query language. But basically, if we have our initial input call tree that has, in this case, a lot of the different Roger Performance Suite kernels, and we only want to look at the ones that were run with the base CUDA variant, then we can filter on that. I'll show the steps. So if we filtered just on base CUDA, this would be our output call tree. And then if we want to say we want to look at any of the base CUDA nodes that are run with a block size of 128, we can then filter even further and grab only the data that was run with block 128. So we write a query that filters this table or this call tree, and our output call tree is only the data that includes the block size of 128. Okay, a little bit more on the top-down analysis. So if we want to visualize this top-down analysis, basically what it is using hardware counters to identify different bottlenecks in your code. So the 4 top-level categories for where your bottlenecks are retiring, bad speculation, front-end bound, and back-end bound. Back-end bound can sort of, probably what you hear about the most is whether something's memory bound or core bound. So those are both back-end bound sub-levels. But basically we can use the PAPI metrics to determine where these bottlenecks are in the application, or in each of the kernels in this case. And the paper is here. So if you look at the slides, you can grab that if you want to learn more about top-down analysis. So Caliper has a top-down module that can derive these top-down metrics for the different call tree regions. Okay, so Thicket has a tree plus table visualization that actually shows these top-down metrics as stacked bar charts. So each of these, okay, let's see. So each row is basically for each of these kernels or these nodes in the call tree. So AppsVol 3D is this row here. The colors correspond to the different bottlenecks. So red here is back-end bound. That's the most significant. Blue is retiring. So we can see these bar charts, and actually each of these bars is a different profile. So we can see the x-axis, the larger x-axis here is the problem size. So we have 1 million, 2 million, 4 million, 8 million. These are our problem sizes across that way for each node and each profile run vertically. And so what's really cool about this visualization is you can really see visually what's happening. So for example, AppsVol 3D, which is this one, is the most retiring bound of all of these kernels. So we see more blue here. And then hydro, lcals, and stream dot. We can see as we scale the problem size, they become more back-end bound. So we see more red taking up a higher percentage of the time than the blue, which is indicating the retiring. So as we increase the problem size for these two nodes, we can actually see that the bottlenecks are changing, shifting slightly. So especially for this Hydro 1D, you can see that pattern pretty clearly. Okay. So as I mentioned, Thicket is written in Python, so we can leverage a lot of different third-party Python libraries. So scikit-learn has a lot of different machine learning and other like clustering algorithms that we can utilize. And so this is an example of the clustering done with Raja Performance Suite. So first we selected the data of interest. We looked at the 8 million problem size, and we used the query language to extract only the implementations of the stream kernel. So we're just looking at the stream group. If you remember, we had like the apps group. There's a stream group, which includes these 5 stream kernels. You can normalize the data, and then you can apply scikit-learn clustering to these top-down analysis metrics to determine which optimization levels basically are grouped together. So, okay, so this is cluster 0 is the circles, which are here, which includes kernels with all 3 of O1, O2, and O3 optimization levels. Cluster 1 is the X's over here, and you can see that those are all the O0 optimization levels. So those got grouped together. And then we have group 2, which also had some of these. And that's both for retiring and backend bound. You can see that cluster 1 has all the O0 optimization levels. And we just show retiring and backend bound because the other values for the Intel top-down analysis were pretty negligible. So in this case, these were more interesting to look at because these were the significant bottlenecks. So yeah, basically what we see here is that the O2 optimization level, which is the yellow, produces like the best performance. So if we see the speed up here is on the X for all the kernels. So the speed up for the O2 in the yellow is, slightly higher speed up value in all of these cases for each of the stream kernels. So that's interesting to know which optimization flag is best for these particular kernels. Okay, our second case study is on Marble, which is a next generation multi-physics code, also here at Lawrence Livermore. For this data, we have 60 different profiles. We ran on 2 different clusters, so RZ Topaz and also the AWS parallel cluster. So we can see those here. We used 2 different MPI libraries, 6 different node and rank counts, and then we actually did here 5 repetitions of each run configuration. So basically, this is helpful to look at, like, if there's a lot of performance variability, like if anytime you run your application, getting some sort of noise measurement or average can be really useful. So running multiple of each configuration. So again, we use that to compute the noise. So let's see what's happening here. So here's our different MPI world sizes, so number of ranks that we ran with. So what we can do here is we can use a group by to sort our data based on the rank count. So basically what we end up with is unique subsets of data for each of these repeated runs based on the MPI rank count. So you can see here on the right that we have our profiles now grouped together by, a rank count of 36, MPI world size of 36. So we can group those together so that we have the different run times for all of those and compute the noise there. Then we can compose these runs across the different platforms and at different scales. So if we want to, then generating a strong scaling plot can be done with matplotlib, again, another Python library. And so here you can see the shaded is the noise, basically, and the dots are the average of 5 runs. So yeah, basically we're seeing here the Intel MPI is dotted in blue, and the Open MPI is this one and the gray. Let's see, was there something else on here? Yeah, so the group by really helpful for being able to compute that noise and looking at multiple runs of the same configuration. Okay, another third-party library that we can use is XtraP. XtraP is an analytical performance model or derives analytical performance models. And so we can use that to analyze an ensemble of profiles that are in our Thicket and look at across different parameters and try to extrapolate how our application will scale. There's more about XtraP here at their GitHub. But to start, we can select functions of interest. And so in these use cases, we were looking at the mult function down here. Oh my gosh. Okay. The mult function, and the red is basically the average. The red dots are the average of each of those 5 runs at the different MPI world sizes, right? Number of processes. And the blue line is the XtraP analytical model that is derived from this data. So the blue line extrapolates, okay, if you increase the MPI world size, here's the predicted performance based on the data you have. So really useful for generating data, smaller amounts of data, maybe at smaller rate counts, and extrapolating what the possible speed up and performance might be at other rate counts as you scale. So here we see that also that the marble mult function is a little bit faster on. So this on the left is AWS, and on the right is is Topaz systems. And we can see it's a little bit faster on AWS, but they scale pretty similarly. There's not a lot of difference in the scaling behavior. Also of interest is visualizing the metadata with these parallel coordinate plots. So these are actually, if you generate the parallel coordinate plots in Thicket, these are actually interactive plots. And you can look at the relationship between a lot of different variables and, for example, like runtime parameters and performance data, and see how they affect like the total runtime. So on the top left here is a scatter plot showing the runtime on the y-axis. The total runtime and the number of elements, or like the problem size that was used. And then on the right, we can see this is the MPI world size and the total time run there. And in this case, I think these plots they start out grayscale, but you can click and drag and select points and decide to color by a certain metric. So in this case, they are colored by the system. So the orange is Topaz and the blue is the AWS cluster. So you can easily visualize which system has better performance, and also another interactive portion is changing what's on these axes. So you can change the X and Y axes, I believe, for all of these. So you can look at how different parameters affect that runtime. Okay, and then on the bottom is the parallel coordinate plot that, so see, how do I start? Okay, so the architecture is indicated here. Topaz is on the left in the orange, and the AWS cluster is on the right here, colored blue. And you can really look, we have the MPI rate count as this row, the wall time, and then the problem size. And so basically how this works is you can draw a line and look at, or follow one of the lines, the Topaz architecture for a certain rank count at has a certain wall time, completion time, and you can compare that with the other architecture, which is the blue line at that point. So kind of what we're seeing here is if you're looking across the different MPI rank counts, the blue is typically smaller in wall time than the orange. So this meaning, again, kind of showing up here as well, the same information just in a different way, that the runtimes on the AWS cluster were faster than on the Topaz. Okay, that makes sense. So as a summary, Thicket is this Python toolkit, open source, for exploratory data analysis of multi-run and multi-platform data. So if you can measure your code with tools like Caliper Insight and put those into a Thicket, then you have access to all these different analysis capabilities. Okay. One plug for those of us at Lawrence Livermore: if you are using the LC systems, a lot of this is sort of automated in a way that's available to you to use. So if you instrument your code with Caliper, and then at runtime collect the performance metrics and metadata using Caliper, those data files are stored on LC systems. And LC has support for a Jupyter server, which basically has access to all of your same data that you generate here. And so wherever those Cali files are, you can actually load them, start up a Jupyter notebook, load them into your notebook and create a thicket and do your visualization and analysis. So part of this is sort of automated for you and that you can access this data. And here again is where the metadata is very important, is if you are generating a lot of different, if you're running your application and generating a lot of different Cali files, you can just put them all in the same directory, and you can use Thicket to filter based on, okay, I want more, I want things launched recently. I want things launched by this user. I want things launched on this system. And so it reduces the need for you to manually manage and organize a lot of those performance profiles yourself, because you can store them all together and then you use the metadata to sort through what was different about each of those runs programmatically. So yeah, really great that we have this capability here at LC. Okay, it's time for the tutorial. Again, okay, I need to share my URL, but all the materials are here at this GitHub link. So we're not going to get through all the notebooks today. We'll probably do one, maybe two. And then if you want to do them all on your own, they're all included there. So this includes all the Jupyter notebooks, a Thicket install, as well as the Raja Performance Suite datasets, all in a self-contained environment. So if somebody can post the Google Doc link in there, we will go there to sign up and I'll show you how we do that. And yeah, I guess my thing is here, we're going to be sharing instances, which means that we're sharing the Jupyter server. And so before you run any notebooks, please just make a copy of it so that you're not interfering with other people's notebooks. So if you just make a local copy, then you won't have to, then if you run cells, you won't be messing up other people's. And then if you can, again, if you want to join our mailing list, that link is here. Okay, let me switch over to this and I'll just remind you how to log in. So again, if you haven't signed up for a slot yet, you don't need the username this time, but you will need to know which row you're in because this is the instance that you're accessing. So for the Thicket tutorial, you will go to the URL associated with where you put your name. So I'm here in this row and I will just click on the link and hopefully these are all working. I started them earlier. Great. So should be able to get right to this Jupyter server here. I'll explain a little bit about how Jupyter notebooks work in case anybody hasn't used them before as well. But basically, oh yeah, I can make it bigger. I just let that up. Thank you. Much better.
Oh, David, there's a question in the chat, or lively discussion actually, that maybe we can pause to address.
Yeah, sure.
So the question has to do with CI and attributing performance changes to code changes, right?
Mm-hmm.
And so I don't know if our participants are able to speak actually, but let me take a stab at it. And I don't, I need to figure out a way for me to let us know if the answer I'm giving you makes sense. So Cyrus is correct that we would need to basically have a way to propagate what has changed into the metadata somehow, right? So if you are, able to propagate maybe I don't know if it's a new version of the code, but if you're testing, I guess, a new hash, a new SHA in your repo or something like that, right? Perhaps that information can be propagated so that we know what version of the code ran. So we can start thinking about that correlation. However, there is also a huge, huge, huge challenge that is not trivial to overcome for this, and that is the performance variability run to run. So first of all, if you were to be doing a multi-node test, you're at the mercy of who else is using the network on the machine. And so repeatability or reproducibility there is not something that you can really expect um, unless the machine's quiet, right? Which never happens. So you would have to carefully think about which tests you're running to start, right? Perhaps single node tests might be more feasible. Even there, though, I will have to caution you that there is maybe on LC we observe basically a 20% variation between the nodes. And that could be, time of the day, that is the node in a bad state? Is it slightly warmer? All the things, right? And so if you have single data points like that, one per day, chances are you're not going to be able to make heads or tails of it either. One thing that we have thought about trying out is basically if your CI indeed triggers these runs, perhaps you can basically on the same node at the same time run one version of the code and run the new committed version of the code. So at least you're reducing, you're taking out some of those variables, right? You're running on the same node at the same time. So hopefully it is, it could be closer to being in the same, looking the same performance-wise than, two random nodes on the machine 24 hours apart. So I don't know. I know that's not a satisfactory answer, but does that kind of make sense? And yeah, what would people like to do with that? So Jeff, the code version is in the metadata. Does that mean every commit? Okay, I don't see an answer from Jeff. So okay, so let me address Jeff before I read more comments. So Jeff, I think that is certainly possible. One of the things that we're working on is so you recall the spot data, and that's somewhat limited in what it is that how you can look at the data, right? It doesn't quite have the full capability we do here. So we are working on this. This is probably I will take a note to push your interest up to Matt Legendre, who's spearheading that. But so if that is that is all you want, I think that this is something that we will be able, a capability we will be able to give you fairly soon. Now, again, no guarantees of how much variability you see and whether the data will make sense, right? That's the trouble, but the capability is coming. Okay, so I was trying to understand what Aaron is saying. And Christy, do our participants not have an ability to speak? Is that out of the question?
They should.
Okay.
I thought that they would be able to unmute.
So, right. So, Aaron, the way this works, yeah, I don't know. Are they saying they can't? Darn.
Yeah.
That's too bad. So I think I can address this though. So Aaron, sounds like you are doing this comparison over time. You can do the same thing with Thicket already. Basically, you the piece that is missing currently, you would be reading in, let's say, data, all of the data in the in a directory, right? And so you might be looking at you could sort it by the date, and look at that comparison that way. You probably want something more like a sliding window for this, or some modification of that, right? You don't really, on a daily basis, you don't need to look at 5 years worth of data. You probably only want to check, the last couple of months. So a sliding time window is something that we still need to work through for that. But technically, you can do that, right? So anything that Letitia is doing with a Python script um, is is basically, we have a equivalent capability, but what you're probably not describing here is how does she decide which of the files to read and how to do the comparison, right? So that's the piece that the human needs to be able to do and automate, hopefully, right? And so, yeah, maintaining the script. And so, yeah, that is a common pain point. We can have basically notebooks that do things, right, but maintaining those notebooks and testing them, right, and then making sure that they are working correctly is a challenge for any notebook based scripts, right? Okay, so it looks like Jeff does have a proxy for the hash. So yeah, Jeff, you should be able to do that. The trouble right now is reading in only what you're interested in, right? Not you probably don't want to read in everything. So Nick, if so sounds like you know what you want to be looking at. And so we do actually, I don't think we had figures on this, but because, once the data is read into Thicket, it's Python, right? You can use any Python library from there. We have plugged in and played with specific libraries, um, such as scikit-learn and others. And so basically, once you have the data and you know which metric you want to be studying, right, you can perform any analysis that somebody has implemented in Python, right? Even it doesn't have to be implemented in Thicket, right? If regression analysis libraries exist, you simply take the data. So Thicket reads the data and helps you find that metric you're looking for, and then you can do any analysis on that data with any Python library. Okay. Yeah, so I'll take your note for Matt as well, Aaron, about the sliding window. Yeah, and yes, absolutely. So sounds like she's doing something equivalent under the hood, right? So we basically have probably automated a portion of what she's doing in her script. And so in general, that simplifies maintainability. I know that Letitia was talking fairly frequently with Stephanie in the spring. So it sounds like when Stephanie is back from her maternity leave, we should circle back and tie up loose ends and hopefully simplify that process for you guys. Yeah, Kenny, I think I would be interested in understanding better what would actually be helpful to point you back at the code, I think is what you're asking. Okay. Should I think maybe we have handled the questions. I don't see them rolling in as much. So maybe we can go back to the demo.
Okay, sounds good. Yeah, we'll start with the demo. And maybe it'll help answer some questions too if we have more examples of things. Or maybe it'll generate more questions. Probably the latter. Okay, so in your Jupyter server, hopefully everybody has been able to access. If not, let us know. But you should be seeing two folders, the data folder, which includes the Raja Performance Suite performance profile data. So you can see like for Lassen, certain compiler. I want to, here we have our Cali files, right? So you don't need to mess with these. These are just there for the analysis. In our notebooks folder, you'll see 5 different notebooks. Again, please just, in case you're sharing an instance with somebody else, just make a copy. There's 2 ways to do that. You can select it and then hit duplicate here, or you can open it and then say make a copy. But the easiest way here is to just say duplicate, and we'll say duplicate. That way you won't be running into somebody else's. And then you can just click on it to launch it. So we'll start with 01 Thicket tutorial. So if we want to follow along, we can go in there. And if you're not familiar with Jupyter Notebooks, basically you can run your Python code in here along with markdown text cells. And you can render all your output right here in the notebook. So Jupyter Notebooks are really great for reproducibility, also iterating on maybe like a plot. If you are generating a graph and you need to see it immediately and you want to just make little tweaks, really helpful for that kind of thing. So really great for the exploratory data analysis, because a lot of the functionality for things like interactive plotting and some of the Python libraries work in Jupyter. So, and again, LC has a Jupyter server, Jupyter Lab, I think, actually access, where you can look at all the files on LC and access those and run Jupyter Notebooks, pointing right at your LC file system. Okay, so we'll start here. We'll just go through some of the sort of basic Thicket tutorial 101s. The first thing to do is to import necessary packages. So you will notice here that you do have to import Hatchet. So some of the functionality is still within Hatchet. And so we have both Hatchet and Thicket here. So we can actually run these. Oh yeah, and then just a shortcut for running, you can either say, click the run button here when your cell is selected, or you can hit Shift Enter, and that will run that cell, and then go to the next one. And then also another tip for Jupyter Notebooks is a lot of times they're dependent on the order that cells are run. So if you're hitting errors later down, it might be that you just need to rerun from the beginning. So you can come here and say cell run all, or you can, probably best to just say cell run all, and it'll rerun from the beginning and reload your data. So if you do hit errors, try that first. That might be the reason that you're getting them. Because a lot of times the data frames are changed, and if you didn't run the cell above, then you might hit an error. Okay, we're disabling some Pandas 3 future warnings for now. That's something for us to worry about. You don't have to worry about that. And the first thing we do is we read in our performance profiles. So in this case, we had 4 different problem sizes here, and our data is located in these folders. And so here we're just iterating over the different problem sizes and loading each of those in. And we're going to have a Thicket object that has the different problem size data from, for this one. And then we're also going to create a Thicket object with this file and adding this one together. Okay, yeah. So it's both of these together in the second one. Okay, so we'll run that. You'll see it reading the files in. If you're just curious to find out more about what a function can do, we have this, you can just call help and then pass in the function. So what does from Caliper reader do? And the docs will pop up here right in the output. So really useful when you're just trying to explore your data and see what things are possible And then we have our Thicket components, which we're going to display here. So the main or the table that we talked about is the performance metrics table. So here's our Thicket object. And then to access the performance metrics, we just call the data frame component. And you can print it this way, which helps just with the rendering. But you can also just print it as you would any pandas table with just thlesson.dataframe or print dataframe, etc. So there's a few ways to do that, but this is what we do here. And you can see here each node and the profiles that they came from here and how they were composed together, right? So each node has each profile added. And then we have the associated metrics. So performance metrics are minimum time per rank, max time per rank, average time per rank, the block size, some of these other Caliper metrics, bytes per rep, flops per rep, etc. So you can kind of scroll over and see, and then the name here of the node. I'm gonna go over every single one. And then, okay. So I'm going to make this actually slightly smaller. It's a little hard for me to see everything. Okay. So now we can look at the call tree. So to visualize this, we look at the Thicket object and call tree, and then we can specify which metric column we want displayed here. So that's this value that we're looking at, the numeric value. And then this is the node name. So you'll see here we're looking at average time per MPI rank in each of these. We have our parent, and then we have all the different groups and the Raja Performance Suite kernels here, and the average time per rank for each of those. So lots of different groups there. And again, this is the default coloring, but that can be updated. Okay. And then if we want to just look at a specific profile, so one of the profiles we loaded in, we can filter because it's a data frame and that's one of the indices. We can filter just based on that profile ID. So again, if you have a lot of different data in on LC in a folder and you just load it all and then you realize you need to filter down and look at specific things, one of the ways you can do it, just filtering by specific profile. Okay. Then we get to the metadata. So the metadata is also a data frame, but we access it by calling the Thicket object or calling metadata component on the Thicket object. And again, here, a row is a single execution of the application and has, sorry, this one looks a little weird because they're big names, but it has a single profile index. And then we have our metadata information stored across. So if I scroll up here, you can see a lot of these Caliper metadata metrics from when Spot is sort of getting phased out, but that name is still there. And then the command line, so how you ran the application, the Raja version, CMake build type. I mean, you can, a lot of the metadata is automated, but also you can add more that's custom to what you want to look at. So, OpenMP threads, number of threads, etc. Problem size. So lots of things there. Variant and tuning are Raja Performance Suite things. So variant is the programming model and tuning is like something like block size or something like that. So different parameters you run. Okay. So if we want to filter the metadata table, we can filter here. We want to say we only want the data for when our problem size was 1 million. And so we pass this problem, this Lambda function that filters basically, give me the row if the column name problem size param, if that value is equal to this. And then we pass that Lambda into our filter metadata function, which we can call on our Thicket object, and we generate a new metadata our new Thicket object, and it has the metadata table that just shows the problem size of, well, we have to scroll over. It's over here. Yeah, problem size here, and they would all be now the 104, 1 million problem size. Okay, we can also do group by using the metadata. So if we have, let's see what we're doing here. Oh, so we can say like, we want to look at only data that was, or group by the day that it was launched and also the problem size. So we want like different indices. Then we can create new tables from those. So now you'll see here we have 4 different thickets created. And the first one is launch date of here and the problem size of 1 million, which is here. And then similarly, each of these thickets below has the different launch date grouped by the launch date here. So that can be useful. I'm relating to the CI if there was a new version. When did something run? You know, looking at something that was run more recently, or something in the past. Okay. And then we want to look at our aggregated statistics table. So I mentioned the 3 components: the performance metrics, the metadata, and the aggregated statistics. When you first create your Thicket object, the aggregated statistics table is empty of actual metrics. You just have the node that corresponds to the call tree and the name of that node. So we have those here, but you'll see that there's no other things. But we can look at it. It's called the stats frame, is the aggregated statistics table. And the stats frame is actually also a Hatchet graph frame object. So the stats frame contains a graph and a data frame, or a tree and a data frame as well. So similar to the this, you know, I don't know, higher level Thicket object, I guess, where you can say Thicket object data frame shows you the performance metrics. You can call stats frame data frame to look at these metrics, and then I'll show you how you fill in this table in a second. And then you can also visualize the tree by just calling tree here, which I think we have an example of in a second. Okay, so we can filter the aggregated statistics. Let's see what it's doing. So if we only want to select certain nodes, we only care about the Rajaperf algorithm and stream multiply nodes. We can just specify those exactly here, what we want to look at, and then we can again pass the lambda function filtering by those particular values in the name. And so we can see here that now our statistics table is smaller. Okay, and it contains only those exact nodes. So now we fill in this table by calculating some actual aggregated statistics. And we can calculate, for example, like the mean and median of the performance data. That's so basically what happens is the operations are performed on the performance data and then appended into this aggregated statistics table. So because it's an order reduction, you're taking multiple profiles that are in your performance data, and then you're, you know, aggregating some metric, and then you're putting one value per node into your aggregated statistics table. So we can see here the median is now appended as total time underscore median. So we, oh yeah, sorry. And you specify the metric here with total time. So if you say, I'm going to look at the total time metric, calculate the median, and that gets appended to your stats frame. And then similarly, with the mean, you can do the same thing, and they'll just keep getting appended to your aggregated statistics table. Some other functionality we support is calculating percentiles. So looking at the total time metrics again, we just call the stats function percentiles. And you can see here you get the 25th, 50th, and 75th percentile for each of those nodes. Okay, so now, so I mentioned that this aggregated statistics table is a graph frame, which means that it has both the data frame and the tree visual or components. And so you can visualize the tree by, again, the same way that you normally visualize the tree, except for you have stats frame here to indicate you want to look at the stats frame tree. And then again, you specify which metric column you want in the slot here. So now we're looking at the median total time for each of these nodes across all of the profiles in our data frame. Okay, I'll continue. Okay, so the query language, we had a small example in the slides, but we'll show how that looks here. So here's our initial call tree, looking at the total time. Again, we're back to the performance data table. We're not looking at the aggregated statistics anymore. So just want to point that out. And then in this example, we want to select only the parents and children of the algorithm nodes. So, and basically maintain the structure of the call tree. So we're going to match, the specifics of this are I think there's more in the query language notebook and also in that paper and in the docs. But we basically build this query and can then pass that in using the query call and filter the tree that way. And just a little note, you might see, I can't remember if I filtered it out or not, but there is a deprecation warning. So we actually just changed how we call the query from Hatchet to now it's going to be just query and not query matcher. So there's some changes coming that are just not fully released yet. So if you see a deprecation warning, that's why. But not to worry, we're working on that. Okay, so we filtered, or just as a reminder, here was the initial tree, lots of different algorithms here. And our new tree after that query looks like this. So we have just the parents of algorithm itself, and the children, maintaining that call tree structure. Another example, if we don't want the parent node, we change the query. So now we don't, we're not matching anything anymore with the star. Oh, here we go. Here's this deprecation warning I mentioned. And yeah, so we pass this new query in, and this one selects just the node itself and the children and not the parent node. So we can see that we filtered out the initial Raja-Perf's parent node from this tree. All right. Yeah. Okay. All right. So another useful plot is the histogram. So the histogram basically allows us to see like how many occurrences of a certain value there were within a certain data set. And so, for example, you can look at the help function here. So if I know that I want to display histogram on my stats table, or do the stats function, then I can see what things I need to pass in to get that to work. And then I'm just grabbing the Raja-Perf node again. So just the first node in that filtered list from before. And you'll see that here. So in this case, we're looking at the total time. So basically we had the count is on the y-axis here. So we said we have two nodes that had a total time within like 2 to 6. And we had one node that had a total time between 6 and 10, and one node that had a total time between 10 and 14, or whatever. I think these are scaled slightly, so. But, Yep, so that can be useful to see how quickly are things finishing, or and then we can also do a heat map. So again, you can look at the docs with the help function, and the heat map, similarly to the histogram, kind of shows you the count of how these are happening, but with colors based on the value. And so this one, again, we have on the, I'm going to go zoom out a little bit so you can see the whole thing. It's really big. On the total time. And so, yeah, so the total time, and we're looking at here, this is the higher level algorithm node. So this one took the longest because I think it includes the actual runtime for all three of these. But then you can see which of these actual kernels, these are the three different kernels under algorithm here. And the darker values were faster and the lighter values were slower. So you can really sort of visualize across your functions what was faster or slower. And there was, what we've kind of learned through this analysis is that if you have really, it can be helpful just to look at maybe a couple metrics on the x-axis. Like here we have the total time median. If you look at a lot of different metrics for a heat map and the values are really disparate, the scales can just get really unwieldy, and then you end up with just like maybe a lot of white or a lot of black, and it's hard to tell the difference. So we found that it's a little bit more helpful to just look at maybe a few metrics this way, unless your numeric values are similar across the metrics. Hopefully that makes sense. Okay, so here's some examples for how to concatenate multiple thickets. So there's a few different ways to do this. Again, we can like compose the data into thickets and then add those together, or not add them together, but combine them. So for example, here we're looking at the different block sizes for each problem size in our data that we ran on Lassen. So we have, the CUDA block size that we passed in here, and we're reading in the thickets. So we basically created a thicket for each block size, and each of those thickets has multiple problem sizes. And then we can concatenate the thickets together here with this function and look at what that looks like. Let's display it. Maybe we're hitting the limits of AWS. Oops. Okay, here we go. So does this look right? Let's see. I was expecting. So okay. One second. Oh yeah. Okay. So I don't know where the block size went here, but I was thinking of the next one. Oops, sorry. Oh, block size is here. Okay. So basically we can concatenate these together and on index. Oh, I see. Okay. On the profile. Yeah. So on the index, we concatenate them together and we have our block size function here. And so basically we now have a column for block size and these. Another way to concatenate them is to do this column-wise. This is what I was thinking of. And so here again, we have our different block size thickets, and we're going to concatenate them with different headers and display that one. And you'll see that there's an additional sort of column that shows the block size. Okay, yeah. So in this one, you can see we indexed, or the metadata key here is the problem size run parameter. And then we have here all of the block 128 data. And then we have basically extended and repeated for data with block size 256, etc. So you can scroll over block 512 and block 1024. So just different ways to concatenate the data and have like a slightly different structure that might be useful in different things. There's also the last example is to concatenate with group by. We can look at the tuning. And so again, we see that 4 thickets were created with the different tunings. And we concatenate them together. And can show the data. Okay. Yeah, so the result is similar here because we're saying the headers are the keys, which is that block size, and which is the tuning. So the block size is the tuning is the Raja Performance Suite word that encompasses changing parameters such as block size. So that's what we're seeing here. Okay. That is the first notebook. That took a little while. I'll probably just briefly go over the second notebook and talk about what's in these other notebooks. I don't think we have time to go through everything super in detail. But if we look at what notebooks are here, again, there's that Thicket 101 sort of tutorial that we just went through. We have a clustering example notebook as number 2. Number 3 has some examples with the extra P analytical performance modeling. Note on this one, we have a unmerged pull request that basically will update and do some fixes with Python versions. So when you get to the end of this notebook, you might notice there's an error. Basically, we need to do a couple fixes, but you can actually view some of the output that would be from this on our Thicket docs. And then we have the stats function, so a lot more in detail about all the different statistics analysis that you can run on your thickets, as well as promised, more detail about the query language. So a lot more examples for how to write queries and what kinds of filtering you can do with those queries, which are pretty powerful. So I will briefly go over this. Oh, I didn't follow my own advice, which was make a copy. So let's do that. Okay. So again, we talked about the clustering in the overview presentation. And so here's basically the example notebook for this. And as you can see here, based on our imports, we have kind of our typical ones, but we're also pulling in these other Python libraries. So scikit-learn, all this clustering. So again, like Olga mentioned, basically the fact that Thicket is in Python opens up pretty much any Python analysis that is already implemented. So there's a lot of data analysis that has been implemented in different Python libraries. So, I think you can kind of go crazy with that. If someone's implemented something, you can try it. And then I will go through these. We have a lot of utility functions that we've created. These are a little bit, they're kind of a lot, but these are things that you would be free to use and manipulate and change to help you do your analysis as you see fit. But these are just some examples of how like the clustering is done. So we have some utility functions for like manipulating the performance data. So getting the leaves, only the leaf nodes of the thicket. So again, this is using the query language. And we're just filtering any thicket we pass in to only get the leaf nodes. Okay, so that's what's happening here. So a lot of these things you don't have to write from scratch if you want to do some data analysis, but aren't sure where to start. Also then, applying that, I think that was, applying the query to the thicket. So you write your query and then you apply it. We have get node, which basically just says, give me a thicket and give me a node name and just give me the node associated with that node name. So And then nodes in group, so matching like the upper level if they're grouped by a certain thing, or their parent, basically any nodes that share a certain parent. Okay, so those, I can't remember if I ran the cells, so I'll do that. And then a few other checks, check for optimization level. I think this can either be a string or an int or something, which is why we have these two ones. And then adding metadata to the thicket. So this is useful because you can actually take data from that's in your metadata table and put it into your performance metrics table, and then do your analysis there. So if for example, if the optimization level is in your metadata, you can actually put that into your performance data, so you can do some other analysis. Collecting ensemble data. Oh yeah, so just creating a thicket from multiple profiles here. Just another way to basically concatenate. And then I thought some of these were labeled. Okay, yeah. And then we have some speed up calculations. So looking at the speed up based on optimization level, just another utility function kind of specific for this notebook. But could be used otherwise. Building the data frame from the clustering, which we'll call later. Normalizing the data. So again, like if the scale of your numeric values is really, or there's a lot of outliers, or it's just a really vast difference, you may want to fit that to like a standard scaler, or and to basically help reduce like the effective outliers when you're performing clustering or other machine learning things. And then the actual clustering function, conducting the k-means clustering, which I'll run. The silhouette test, I believe, is just determining like a good k value. And correct me if I'm wrong to who wrote this notebook, but I think it's just determining a good k value and determining if the clustering is worth it. Okay. And then plotting. So that's pretty self-explanatory. But matplotlib is fun, so. Or I guess this is using Seaborn. Okay, and also plotting, yeah, here. Again, so these are all things that you can feel free to use. We'll just go through this quickly. Okay. So we're reading in our data here. This is data from the CPU quartz runs. And then we want to look at our top-down metrics that we talked about in the slides. And we want to look at the stream kernels, and we want to generate numbers of clusters for each of these top-down metrics. And you read the data into a thicket with this concatenation function that we have. And then I think we just I'll just run this one, but you just run one of the next three. We're just looking at the stream kernels and adding the optimization flags to the performance metric table so that we can calculate the speed up based on those optimization flags, which is done in this version or in this function. And then we build our table. And so now you can see we have our optimization level in our performance metrics. We have our, I see the flag plus the actual number as an integer. And then we have the compiler, the different top-down metrics, and the speed up column, which was the calculating the speed up based on that. Optional normalization. Actually, I'm kind of curious what it looks like if I don't run it. Do the actual clustering. Nope, it didn't like that. Oh, nice. I think it was expecting a normalized data variable. Okay, we can look at the centers of the clusters, and actually this is how, yeah, sorting the data frame by the speed up, yeah. And then plotting. So you can see these got a little squished, but you can see the clusters here again, similar to what we saw in the slides. And front unbound was pretty negligible, if you remember. Same with bad speculation. So really this back end bound and retiring is where we were seeing things. Okay, I'm gonna end here, I think, just in case there's any other questions, and so that I don't keep you all the way to lunchtime. You can, I'm not sure how long we can keep these instances up, but you can probably keep playing around for at least another 10 minutes with these notebooks if you want to. And then again, if you just go to our tutorials, our Thicket tutorial repository, you can do those again and you can run them locally. And there's instructions there with a few different ways. And then if you want the slides from today, they are here at the Read the Docs under tutorial materials. So you can download those slides. Yeah, thanks very much. And if there are any questions, I can stop sharing.
So Christy mentioned the instances can run for another hour probably. So if people are still playing, that's good. The other thing that I'll mention is, so you've got everything going with the tutorial at the moment. Basically the notebooks, you can save those, or you can start with the ones that are posted on our tutorial on Thicket, on the Thicket tutorial on GitHub. But I did want to mention again, and Davey, you already said it, but we do maintain installs on LC.
Oh, yeah.
And so if you go to the Jupyter notebooks on an LC machine, you can open a notebook that lives in your home directory or save one there. And simply point it at our install that's on LC, and you don't need to worry about installing anything else. From that point, you are simply using the notebooks, basically, just like you are able to do right now in the container.
Yeah. Definitely.
And at that point, right, when you're running a Jupyter notebook on LC, so that's got access to your scripts that you're saving in your space. It also has access to the data that you have, under your user, right? The access is controlled with the same Unix groups as access on LC to, files and everything. So, yeah. We try to make it simple. Certainly, if you have questions about that, if the first go around you don't quite follow, please reach out.
Oh, question. Can you use Hatchet without using a notebook? Yeah, so you can actually.
Yeah, so we need to stand up more testing. A lot of our testing is the notebook's capability. There is basically a large subset of functionality is in just Python, and it doesn't require any interactive kinds of things. And so those portions can indeed be run simply in Python. Obviously, there are capabilities. The interactive, specifically interactive capabilities will not work that way. Yeah, if you're only after the Python functionality, you can do that.
Yeah, and I think like the visuals obviously don't look as good, but the trees aren't bad. You can print like a tree in the console without being in a notebook, and that's pretty similar to what our trees look like. But the data frames are obviously harder to look across at the whole console, or on the console versus on the notebook. So, but yeah, they are. You can look at those.
Yep, we went through a fun exercise of helping Los Alamos recently. They were analyzing data that was coming off of Crossroads, and obviously they did not want to take it to a different network. So we stood up just a Python only analysis for them that they could take over to Crossroads, since they didn't have the notebook infrastructure there. So they were using just plain Python version for that.